Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. I'm your instructor, Dr. Twinkle Tripathi. In today's lecture, we'll try to wind up all the mathematical preliminaries that we need to know to understand and be able to analyze more properties of multi-agent systems. So far we have covered various aspects associated with matrix theory and linear algebra, and today we'll get a little bit further into analyzing some more interesting properties of matrices associated particularly with their spectral properties. So let's get started. So we'll talk about non-negative matrices. So what are non-negative matrices? It's a very simple, as the name suggests. A non-negative matrix is simply a matrix A which has all real entries in our case, and every entry of the matrix is actually non-negative or greater than equal to 0. So why is it important to us? Now, to remind you of that, let's again look at this example of the de Groot model, which we have been talking about since the past few lectures. So again, what does the de Groot model represent? What kind of a social scenario? It simply represents a group of n interacting individuals who update their opinions as they talk to each other, following a model like this. This shows an image of a few people talking to each other. Now, in general, interactions, as we have discussed before, can be modeled using graphs, where an edge between any two nodes here represents that there's a communication between them, and every node simply represents an individual. Now, what we can also do further is we can associate a matrix with this graph. What does this matrix represent? It's known as the adjacency matrix. We will talk about it in more details as we study about more concepts from graph theory. But here, let's just introduce what it means. The adjacency matrix simply gives us an idea of which two individuals within the network are communicating with each other. How does it do that? Now, it is an n cross n matrix where n is simply the number of nodes or individuals in the group. And every entry Aij, this is important. If it is greater than 0, it simply means that I is actually taking information from J. Or I basically communicates in J in a unidirectional manner. And if it is equal to 0, it simply means that I and J do not communicate with each other. Now, applying this for every pair of individuals within the network, we have formulated this matrix where, if you see, A12 entry is non-zero. And we can see that there exists an edge here starting from 1 and ending at 2, meaning 1 is actually receiving information from 2, which is reflected here. Notice that in these situations, the adjacency matrix that we get is most of the times a non-negative matrix, right? So, in the study of multi-agent systems, non-negative matrices are really important and can be applied to most of the scenarios. So, there's only one case where the adjacency becomes, it can also take negative entries. That happens when the interactions between individuals become antagonistic with respect to each other, which is something we will discuss much later in the course. For now, let us assume that all of them, when they talk to each other, they are cooperative, meaning whenever one receives an information from 2, it actually updates its own opinion. Okay. So now, since non-negative matrices are something which will keep coming up in the course, we must learn how do we analyze these matrices. And we have already seen that spectral analysis is a very important process which helps us actually study the emergent behaviors. But before we do that, we will focus on two very specific kind of non-negative matrices. The first one being an irreducible matrix. So what is the definition of an irreducible matrix? Now a matrix A is said to be irreducible if, first of all, it's a real matrix, a real square matrix, and there does not exist a permutation matrix P such that whenever we do this operation PAP transpose, it becomes block triangular. Such a P should not exist which can make PAP transpose block triangular, meaning this. What is P? P is a permutation matrix which is constructed by simply shuffling the rows of the identity matrix. So whichever way we shuffle it, so obviously there are n number of permutation matrices that one can construct, and for each of them, this operation should not make a block triangular. Then it is known as an irreducible matrix. There's an alternate definition to it, which is, again, a matrix A is irreducible if this summation, this is simply the summation of the powers of the matrix A. The summation starts with k equals 0 and goes up to k being equal to n minus 1. This summation should be positive. Then the matrix A is irreducible. Note that since we have not yet related these definitions to graphs, it might be a little bit difficult to visualize what they in reality mean. But from a graph theoretic perspective, these matrices have very interesting properties, which we will talk about in more details eventually. But let us quickly see an example. Suppose we take this, we have some graph, and this is its adjacency matrix, which takes this form. Now, let us start by taking the sum of powers. Note that here n is equal to 3, and we need to take this summation a to the power k, where k starts from 0 and goes up to n minus 1, which is equal to 2. Hence, we have I plus a squared. Now, if we do this operation, one can easily verify that this summation is greater than 0, meaning the matrix is actually irreducible. Let us take another example. Here, for this matrix, if we do the same operations, let us sum of the powers. What we will see here is, for this particular matrix, the adjacency or the matrix A is actually reducible. Why? Because this summation now becomes greater than equal to 0, which violates the definition of irreducibility, meaning this matrix is actually a reducible matrix. Now, similar to the notion of irreducibility, we have yet another kind of a non-negative matrix, which is known as a primitive matrix. Now, what is a primitive matrix? Again, it's a real matrix, and it is primitive, first of all, if it is non-negative, and there must exist some integer k, a positive integer, or a natural number k, such that a raised to the power k should be greater than 0. Let us see some more properties of it. Note that if we have found some natural number k for which a raised to the power k is actually greater than 0, then of course all subsequent powers of the matrix become positive. Why? Let us see a quick example. Let us denote a raised to the power k with this. And let us multiply with a itself, which is see, since this is a non-negative matrix and this is completely positive, when we start adding it up, it can never annihilate or completely make the entire, let's just write one of the entries. The first entry is simply summation of this should be P. Now notice that this summation obviously can never become 0. Hence, and the same logic will apply to every other entry, meaning this entire product will again become greater than 0. And we can keep doing this iteratively and we'll observe that obviously every other power also becomes greater than 0. Yet another interesting property is that whenever a matrix A actually is primitive, it naturally becomes irreducible as well. So again, in the sense of graph theory, these properties of irreducibility and primitivity have very nice meanings, and they help us prove which kind of network configurations or network topologies are actually suitable to achieve consensus. But for now, let's just see an example, and we'll eventually learn to apply these techniques for distributed algorithms. So let's take this matrix A and B, and since we want to study whether these are primitive or not, let's try taking their powers. So when we take A square, we see that A square has become a positive matrix, meaning that A is a primitive matrix. And if we take B raised to the power k, it takes this form. What do we observe here? We see that there's always an entry in B raised to the power k which is strictly equal to 0, meaning that this matrix can never actually become a positive matrix irrespective of whatever value of k we choose. Hence, this is not a primitive matrix. As we thought, A is primitive and B is not a primitive matrix. Let us now see a characterization of the set of all positive matrices that one can take, and where do the primitive and irreducible matrices fit in. So this chart gives the answer. Now the largest set that we have is the set of all possible non-negative matrices. Within this set, the second largest set would be the set of irreducible matrices, and inside of it is the set of primitive matrices. And note that primitive matrices are not necessarily always positive, as we saw in the previous example. Let me show you this again. The matrix A here has a 0 entry, meaning it's a non-negative matrix, yet it is primitive, meaning that the set of all positive matrices actually is a subset of the set of all primitive matrices. So this is the characterization of the set of all possible non-negative matrices that one can construct. So what we'll eventually talk about is how are the spectral properties of all of these matrices related to each other, and are they at all interesting? We'll start this discussion by actually looking at some properties of positive matrices. Now, what is a positive matrix? So, we take a real matrix A and we call it positive when all of its entries are simply greater than 0. Let's look at some of the properties associated with it. Now, we have already discussed this in the previous lecture. If A is greater than 0, then all of its powers will always stay positive, as we can see here. But what can we say about its eigenvalues? Can we say that since all of the entries are positive, that the eigenvalues are somehow real? Or can we say that since all of the entries are positive again, are the eigenvalues always positive? So the answer to this question is no. Positive matrices need not always have all positive eigenvalues. For example, let us consider an A matrix of this form. If we figure out the characteristic polynomial and try to find its roots, it can be very easily checked that the eigenvalues in this case are actually -1 and 3, meaning what we have is a completely positive matrix A, but it can still have eigenvalues which are negative. But can we say anything about the existence of a positive eigenvalue? As we see here, we can see that at least one of the eigenvalues is positive. Now, the answer to this is actually yes. When the matrix is positive, there generally exists, or there always exists, an eigenvalue which is positive. And this answer is given by the Perron-Frobenius theorem. So let us see what is the Perron-Frobenius theorem. Now the Perron-Frobenius theorem gives a lot of interesting spectral properties associated with positive matrices. So let us see what are these properties. Now if A is a positive matrix, then A always has at least one eigenvalue which is completely real. It will also have, so I don't want to say also because sometimes we can have only one eigenvalue which is real and positive. But in general, a positive matrix A will always have an eigenvalue which is both real and positive. As we saw in the previous case, let me write this example here. The eigenvalues were this. So we see that we have our eigenvalue which is real and positive. Now there will always exist an eigenvalue which is farthest from the origin. So we call that eigenvalue lambda p, also known as the Perron root, based on the mathematician who came up with this theory. So that is the eigenvalue which is real and positive. Not only that, so we talked about the Perron root being always real, positive and strictly larger than every other eigenvalue. The corresponding eigenvector also has interesting properties. What are they? So this holds for both the right and the left eigenvectors. It says that the left and right eigenvectors can always be chosen such that all of the entries in it, so both of them will be n cross 1 vectors. Now all of the entries of them have the same sign, meaning if one of the entries here is positive, then every other entry has to be positive, and if one of the entries is negative, every other entry has to be negative. Not only that, we have the Perron root which is real and simple and which is strictly large in magnitude, but sometimes what can also happen is we can have other eigenvalues which are real. Now in those cases what happens is the eigenvectors which we get, should not write it as Vp. Let's denote this eigenvalue as some mu, and V mu has to have entries which have mixed signs. So this is a very strong way to distinguish. If you only look at the eigenvectors now, we can tell whether it is associated with an eigenvalue which is either dominant or it's not dominant. So now these are some very unique properties which, without even looking at or without even calculating the characteristic polynomial, we can always be sure that the matrix will satisfy each and every one of these properties. Now, however, what happens is a lot of these or some of these interesting properties can get lost when we now make the matrix non-negative. What are the properties which we lose? Let's take a look at it. Now, let's start with the matrix A which is non-negative. Sorry, this is greater than or equal to 0. Now, in these cases, the farthest eigenvalue that we have can actually be non-negative. Let's see an example for it. Suppose we consider the matrix. This is now a non-negative matrix. What are the eigenvalues of these matrix? It is simply 0, 0. What we see is that we do not have even a single eigenvalue which is actually positive, meaning the farthest eigenvalue in these cases can actually be non-negative. And in some cases, when we do have eigenvalues which are greater than 0, lambda p, which is the Perron root, they can even be repeated. Again, a simple example of it would be our identity matrix. Here, the eigenvalues are actually 1 and 1, meaning lambda p is a repeated eigenvalue. Okay. And again, in these cases, we need to relax the condition which we had before, like the associated eigenvector, which is Wp, the left eigenvector, and Vp, the right eigenvector. Now, both of them can actually have entries which are they can also take 0 entries, meaning sometimes for a 3 cross 3 matrix, it can look this way. It can happen. Now, this is something which will never happen in the case of a completely positive matrix. Now, in general, when a matrix is actually greater than equal to 0, sorry, there should be a 0 here. Now, in these cases, there are a lot of nice properties that we end up losing as compared to the nice properties which we get for the case of completely positive matrices. However, by adding additional conditions on the non-negative matrices, we can actually retrieve a lot of these properties. So, let us see what are those classes of matrices for which the nice properties still hold. The first kind, as we can see here, is an irreducible matrix. Just to remind you, for an irreducible matrix of dimension n, when we take the summation of its powers, a raised to the power k, where the summation goes from 0 to n minus 1, this matrix is strictly greater than 0. So, any irreducible matrix satisfies this condition. For such matrices, we again have a Perron root, which is now strictly positive and simple. And the corresponding left eigenvectors, let's write Vp and Wp, now they can have all entries of all positive entries. So, when we say all positive entries, note that in the eigenspace, like if the vector Vp has all negative entries, we can simply multiply minus 1 with it and make all the entries positive. But the important thing to note here is that all the entries actually have the same signs, both for the case of the right and the left eigenvector. See, now there's one condition which holds for the case of positive matrices, which does not hold here. What is that condition? It goes this way. So, we say that we have a lambda p, which is positive and simple, and now when we draw a disk or a circle with lambda p being the radius and the center being the origin, now there can exist eigenvalues which can actually lie here, meaning on the circle itself, which cannot happen in the case of a positive matrix, meaning irreducibility comes very close to positive matrices in terms of properties, but there are still areas or properties in which it lacks. Now, these properties can actually be achieved for the case of primitive matrices. In the case of a primitive matrix, we again have lambda p, which is a strictly positive, and so we should also have real here, strictly positive, real and simple eigenvalue. In the case of A being primitive, now lambda p becomes the eigenvalue which is farthest from the origin, meaning if this is where the eigenvalue lies, then none of the other eigenvalues can actually lie on the disk. Every other eigenvalue has to be contained within the disk. Additionally, the properties that were true for the case of an irreducible matrix also hold, which is we can again select the left and right eigenvectors Vp and Wp, which are associated with the Perron root lambda p, such that all of them have positive entries or equivalently entries of the same sign. If you observe, now these are all the spectral properties that we generally associate with the positive matrices as well. Meaning now, while still keeping some entries 0, one can actually construct matrices which have the same properties as spectral properties, as the case of a positive matrix. Let us see some quick examples of these results. So, we have listed here 3 matrices, and we will try to figure out what are the properties which hold in these cases. Let us see. So, we already know how do we calculate when a matrix is reducible, irreducible or primitive. So, if we do those calculations in terms of the powers of the matrix, what we can find out is A1 is a reducible matrix as given here, A2 is irreducible and A3 is primitive. And what are the properties their eigenvalues satisfy? And this is how it goes. Now, if we see here, the matrix A1 is not irreducible. What happens is, in this case, both the eigenvalues are actually equal to 0, meaning we do not have a dominant eigenvalue which is greater than 0, does not exist. If we come to A2 here, A2 now becomes a matrix which is irreducible, meaning we should have some eigenvalues, at least one eigenvalue which is strictly greater than 0, and as we can see, that happens in this case. We have an eigenvalue which is strictly greater than 0, but since the matrix is actually irreducible, there is a possibility of the existence of an eigenvalue which has the same magnitude, and which we can see here, we have an eigenvalue of magnitude -1. In the third case, in the case of A3, which is now a completely primitive matrix, in this case, we see that we still have an eigenvalue which is strictly greater than 0. Now, as given by the Perron-Frobenius theorem, every other eigenvalue, which is the other eigenvalue is half, should be -half. It strictly lies inside the disk whose radius is equal to lambda p. Now, these are some properties which are very useful in, again, the analysis of the spectral properties, which we will look at towards the end of this lecture. But having said this, let us now move on to some more properties associated with the powers of a matrix. So, again, let us start with a non-negative matrix with some eigenvalue lambda. We will enforce more properties on the lambda soon. And let V and W be the corresponding left and right eigenvectors which are normalized such that this relation holds. Now, note that whenever we are doing a spectral decomposition, we use this normalization rule. So, just in the interest of that, we have chosen the normalized set of eigenvectors. The lambda that is given here, we assume that that lambda is simple and strictly larger than every other eigenvalue. In those if all of these conditions hold, then the matrix A divided by lambda is actually a semi-convergent matrix. Additionally, when we start taking the power of this matrix, then it eventually converges to this VW transpose. So, let us try to apply these results. We talked about the spectral properties of a matrix A using the Perron-Frobenius theorem, and we talked about the application to powers of matrices. So, how are these results actually useful? In order to understand that, let us go back to the de Groot model that we had and see how is it useful in our analysis. Let us consider a simple social scenario when there are only 3 people and their interactions are given in this manner. Let's number them first. So every agent takes its own opinion into account when updating its future opinion, and it talks to both 1 and 2. 2 similarly does this, and 3 similarly this. In this simple scenario, it shows that every agent talks to every other agent, and the model would be, let's say, the edge weight of every edge. So the interactions can be modeled in this manner. X, which is a 3 cross 1 vector, its iterations are simply given by this. Notice that a matrix A here, if you do all the operations we can simply see that it's a positive matrix. And what we already know is, given a positive matrix, the largest eigenvalue which we can get, the largest eigenvalue, if we do the computation, we can see lambda p in this case is equal to 1. This lambda p is also a simple eigenvalue. In our previous lectures, we saw that the solution for these systems are given by this. And the steady state behavior, the emergent behavior, simply equals to x of 0. Now, according to this result, so this says that lambda must be simple and strictly larger than every other eigenvalue. Now, since this is a positive matrix from Perron-Frobenius theorem, we know that the matrix A already satisfies this property, right? Meaning, we can go ahead and directly write this formula. What is lambda in our case? It is simply equal to 1. Then A raised to the power k will actually converge to, let's write Vp, meaning the eigenvector associated with the Perron root or Perron eigenvalue, which is dominant. So it is simply equal to Vp Wp transpose. And if we go ahead and do the calculations, for this particular case, Vp will turn out, we can choose Vp as being equal to 1n and Wp as being equal to 1 by n times 1n. Meaning the solution of this entire conversation that happens between the 3 people, now after quite an amount of time, eventually what happens is that all of the agents actually agree to each other, and they agree on the value which is equal to the average of the initial conditions. Now, this shows us that the analysis that we saw on how to use the spectral properties can actually be used to study the emergent behaviors of a networked system. So, and these are also very useful in designing network topologies that can be used to enforce consensus when we are not getting it. We'll talk about more of these properties in the future lectures, but as of now, this brings us to an end to all the mathematical preliminaries that we needed to know to understand the basic concepts of graph theory and multi-agent systems. Thank you.